Hi class, welcome back. So we want to continue our second time through Maxwell's equations. This time we're looking at them in differential form. So with that continuation, we want to now look at the differential form of Gauss's law for electric fields. Before we get into that, I want to do a quick historical background, again looking at people who were monumental in developing and expanding and continuing the field of electromagnetics. So you should probably be able to guess this one pretty quick compared to or in light of last week's lecture. Education, went to Pembroke College, Cambridge, worked at the University of Cambridge in England. He was a colleague of Maxwell himself and also Lord Kelvin. This is a picture of this gentleman. Surely you know him, or not, if you don't. He is Sir George Stokes. So we just saw Stokes' theorem, so this is the individual that was named for. What are some notable things of Mr. Stokes? First thing is, he did not actually derive the theorem that we just studied that was named after him. Actually, Lord Kelvin did, his colleague. But the reason why it's associated with him is because he used this as a question on the Smith Prize exam in England, and so it was such a, I guess, popular question and the way he formulated it that they ended up attributing the theorem to him. He's actually considered to be one of the first known engineers, at least in the civil side of things, and he did a lot of his work as an expert witness, so he was called in as an expert witness, which engineers many times do in the court of law. And he also made major contributions to fluid dynamics and optics, especially with developing the wave theory of light, which we'll get into later in the course. So again, like I said, we're going to continue in part 3, which is the looking at Maxwell's equations again, but this time we're looking at them in differential form and how we derive that. So like I said, we want to take a look at Gauss's law for the electric fields, so we can recall from previous lectures that we can express that with this equation. And remember, this equation is telling us then if we have a surface that defines some volume, so these are related in that this is the surface of this volume, that if we go around this surface and sum up the displacement current vector that's normal to the surface all the way around the surface, that this should equal to the total charge that's contained in the volume. And that kind of makes sense, if you think about it. If there's a charge inside this volume, it's going to be creating this field, and this tells us that it's the total field penetrating the surface of the volume. So for our discussion today, again though, we're again saying the volume is what's enclosed by S. So we're going to take a shrinking 3D box this time for our volume and surface. So we'll have the sides represented by x plus delta x, y plus delta y, and z plus delta z. So if we do that, we'll also consider this field in x, y, and z, and we're going to say this is the general form definition of the displacement vector right here. So we'll have an x, y, and z component, and it can be dependent on all of the directions and time in each direction. And we're also going to define a charge density. Likewise, it's defined by x, y, and z and time, so it can vary. And then this is kind of a quick representation of our differential volume. So again, we have delta x, delta y, and delta z. So the displacement flux emanating from the box can now be evaluated in pieces where we just do it for each side of the box. So we can do this actually pretty quickly. We can take for the surface side of x equals to x, integrate that, we'll just get the negative dx times the delta y delta z. That'll be that surface. So it's the part of the vector that's normal to that surface. Also in the x plus delta x direction, it'll be positive dx evaluated at x plus delta x, again times that same surface area, because it's just the opposite side, so it'll be the same amount of area. In the y equals y direction, it'll be negative dy because it's pointing in the opposite. The surface vector is pointing in the opposite direction. Evaluated at y, and this time it'll be delta z delta x. Likewise, the complementary side of that will be negative dy at y plus delta y, again times this delta z delta x. That's the square that's sitting in that plane. And then finally, at the z, for the surface z equals to z, negative dz evaluated at z. Again, this surface area is going to be the delta x delta y. And finally, at z equals z plus delta z, again, same thing. This expression evaluated at z plus delta z times the surface area of delta x delta y. So we can combine like terms. We saw for three of the pairs there, they had the same surface area. And so we can do that and come up with this expression then for the sum of the displacement vector over this entire surface. You see there'll be two components, x components with the delta y delta z, the y components with the delta z delta x, and then the z components with the delta x delta y. So that's all six sides of the square. Likewise, we can formulate a expression for the charge enclosed by this volume. It's simply going to be this expression we had for the charge dotted with the volume. So it's just the delta x, delta y, delta z, the length of all three sides. And of course, that just gives us rho times delta x, delta y, delta z. So we can take these two expressions for the left and the right hand side of Gauss's law for E fields, and when we do, we come up with this equation. And as we've done before, we can rearrange and divide through. So this time we'll divide through by delta x, delta y, delta z, so divide everything by that. And when we do, this is the resultant. And again, as we've seen before, this is in the basic form of what we need to take a derivative. All that's left is we need to let the limit for delta x, delta y, delta z go to 0, so we could shrink this volume down to a point. So when we do that, we see here, we go ahead and take the limit. So in this case, it's just delta x, this time delta y, this one delta z. This doesn't vary with the volume, so these are our basic definitions. So we can rewrite this then just the partial of dx with respect to x, the partial of dy with respect to y, and partial of dz with respect to z. Again, this is all just basic calculus, first semester calculus, and it's equal to rho. So now we can play a little, some tricks with this and put it, with the notation and make it a little easier to read. Here we can rewrite that then as the partial of x with respect to x dx. This will be the only part that's executed because we're dotting, so this will be the ax's. Again, with the ay's the only ones that'll contribute there, so it'll be partial of with respect to y of dy, and again partial of z with respect to z. And so this was basically the same equation as I wrote before, but as you can imagine, I did this on purpose because hopefully a couple of things here look familiar to you. First thing is that this is the basic definition of the displacement vector over here, and then this is our del operator that we defined a couple of lectures ago. So that being the case, this helps us to rewrite this by utilizing this del vector as del dot d equals to rho. Now remember before when we had the del crossed with a vector, del cross d, that would be the curl of d. But when we take the dot product, we call that the divergence of d. So if we see del dotted with a vector, we can pronounce that as the divergence of d, or the displacement vector. So the displacement of the displacement vector should equal to the total charge inside of a volume. So this, in essence, is Gauss's law for E fields in differential form. So let's look at a couple examples of how this works. So in this example, we're given some arbitrary vector a, which is just 3x in the x direction and y minus 3 in the y direction, 2 minus z in the z direction. And so we're asked to find the divergence of a, or del dot a. So by definition, we have our del operator and we dot that with our original vector. So when we do, the ax's tells us that we're just taking the partial with respect to x of this part, the partial with respect to y of just this part because of the ay's, and the partial with respect to z of just this part. So that's what we're doing here. So as we do, the partial of this is 3, partial of this is 1, and then the partial with respect to z here is -1. We add those together. 3 plus 1 minus 1 is equal to 3. So therefore we can say that the divergence of this vector A is 3. Another quick example of applying Gauss's law for E fields. Let's just say we have a charge distribution here. So from -A to 0, we're going to have this negative rho charge. And then from 0 to A, we're having this positive rho naught, charge. So this is kind of a graphical representation of that. It's negative rho, positive rho. Outside of these, there is no charge. So, and then this is the mathematical way we could do that with piece milling equations together. So since the charge density is independent of y and z, you can see it only varies in x. So going in and out of the sheet, we're not given any indication that it changes. The resulting field is also independent of y and z. So since the charge is, the displacement vector should be 2. So this reduces our Gauss's law down then to the partial of dx with respect to x is equal to the charge, our rho. So copying this back over, we can now integrate both sides with respect to x to get our displacement vector. So if we integrate this out with respect to x, we just get dx. And so now we integrate rho from -infinity to x. So that just does it all the way along the x-axis. Rho dx plus c. So here in this case, we have some knowledge of this that we can go ahead and understand, hopefully, that this constant of integration, just like we said for the other example we did with this, is going to have to be equal and opposite on each sides of the axis. So that gives us a little insight of what's happened to that. So speaking of that, the constant of integration then is going to be 0, since we do already have this symmetry of equal and opposite fields on the two sides of the charge distribution. So that part is satisfied. So thus the displacement flux can be expressed then with this equation here. So outside of -A to A, it's 0, because there's no charge, so it should be producing no field. So as we move deeper and deeper into this charged field, this setup charge, we should start to feel more and more effects of the field accumulating. So that's basically what this is telling us then. We have negative rho x plus a in the ax direction. So as we get closer to the center, we're going to feel more charge on a test charge, more force on a test charge as we move it in there. And then as we move out, of course, it's plus rho x plus a ax for this region here. And then again, once we get to A, we shouldn't feel any effects of the charge, any field for that. Keep in mind, though, we can get the electric field. This is the displacement field. We can get the electric field by dividing by the permittivity. And again, we'll get more into that later, because that's the permittivity gives us some knowledge of the medium that we're in. So that's the significance of that.